Okay, so we'll talk about the Grignard reagent, how to form ketones using nitrile and Grignard reagent. Now, this is what a nitrile looks like. It is carbon with attached with 3 bonds to the nitrogen. So we have 1 sigma bond and 2 pi bonds, and of course we know that the pi bonds are weaker. And here we have an alcohol chain attached to magnesium and bromide. And to make the Grignard reagent, we will need we will need to mix the alcohol halide with the magnesium and ether. Okay, so here the nitrogen is partial negative and the carbon is partial positive. The carbon is partial positive, so it is deficient, so it's a little bit deficient. And here it is attractive to the nucleophile. Okay, the nucleophile will attack the carbon and breaks one of its pi bonds. So when it breaks one of its pi bonds, you will have here this form called amine. The amine is the Grignard reagent. We will need we will need to mix the alcohol halide with the magnesium and ether. Okay, so here the nitrogen is partial negative and the carbon is partial positive. The carbon is partial positive, so it is deficient, so it's a little bit deficient. And here it is attractive to the nucleophile. Okay, the nucleophile will attack the carbon and breaks one of its pi bonds. So when it breaks one of its pi bonds, you will have here this form called amine. The amine is very reactive with water, so when it reacts with acidified water, it will give me the ketone I need, and that's the mechanism. Okay, so we'll talk about hydration of alkyne to form acetaldehyde and ketone from alkyne. So to form a ketone, we will need an unsymmetrical alkyne, like propyne here. And to form a ketone, we have to break this bond. Okay, so we will add dial H2SO4 and HgSO4. Those are hydrating reagents, and they will break this bond and add water and give me this compound. Okay, it's called 1-propyne-2-ol or enol. It is an unstable compound. Okay, so the H here will shift here and break this bond, so it will give me the ketone. It is a stable compound, ketone or propanone, and it is a reversible reaction. So here it will give me ketoetotomagnesium. Okay, so this is a stable compound, and it is a reversible reaction, and it will give me here ketoenol totomagnesium. Okay, and this is how we form a ketone, propanone, which is a stable compound. So here it will give me ketoetotomagnesium. Okay, so this is a stable compound, and it is a reversible reaction, and it will give me here ketoenol totomagnesium. Okay, and this is how we form a ketone, propanone, which is a stable compound. Okay, from an unsymmetrical alkyne. Here, that's how we form a ketone. And this is how we form an acetaldehyde. Okay, we use this time a symmetrical alkyne, not a non-symmetrical. It's a symmetrical alkyne. Okay, we use an ethyne, like ethyne, and we add our same hydrating reagents, which are dial H2SO4 and HgSO4. They will also break this bond and add us water. The OH will be attached to here, and the H will get attached here. Okay, and will give me this compound, and here the H will shift toward here and break this bond, so it will give me at the end acetaldehyde. This is how we get our hydration of alkyne to form acetaldehyde and ketone. Okay, so here we'll talk about reduction of an ester to get our aldehyde. So we will use diabyl H. This is the structure of diabyl H. This is what we will use to get our aldehyde. And to start, we will start with a simple ether a simple ester called ethyl ethanoate. Okay. And here, when we say it is a nucleophilic, reduction, it is because the reagents here act as a nucleophile. The reaction here happens when the lone pairs on the oxygen attack the pure Al. Okay, when oxygen is attacked here, when oxygen attack it. It turned the lone pairs here into a bond. Okay, so when oxygen attacked the Al, it turned the lone pairs into a bond. And has a formal charge of +1, and the Al has a formal charge. The Al has a formal charge of -1. Okay. Here, when the Al kicks back the hydrogen, trying to go back to just when oxygen attacked the Al, it turned the lone pairs into a bond. And has a formal charge of +1, and the Al has a formal charge. The Al has a formal charge of -1. Okay. Here, when the Al kicks back the hydrogen, trying to go back to just 3 bonds. So where does the hydrogen go? It goes to the partial positive part of the carbonyl carbon. This will give carbon a total of 5 bonds, which it can't have it. So the bond here will break. Okay. The electrons in the pi bond between carbon and oxygen sits as a lone pair here on oxygen. Okay, so after the bond broke, okay, the pi bond broke, the electron in the pi bond between carbon and oxygen sits as a lone pair on oxygen. Okay, so all you will need to do sits as a lone pair on oxygen. All you will need to do is an aqueous solution. Okay, and add water, and we will have our aldehyde. And that's the mechanism. Like that, benzene could react with this form and not this form, because it is a highly reactive intermediate. So the pi bonds here will attack here and neutralizes the oxygen. Okay, and then in the benzene here, just like we said, the pi bonds here will attack and the oxygen will be neutralized. In the benzene here, we have attached this group. Okay, and just like any EAS reaction, we will get the proton on the same carbon as the group. Okay. Okay, and when this bond broke, we still have the Cl, AlCl3 minus. Okay, so these electrons in that covalent bond are leaving with chlorine. Okay, and neutralizes the Al and attack here the H. Okay, and we're gonna form that pi bond. Okay, we're gonna form that pi bond and restore aromaticity. Okay, we're gonna restore aromaticity, and we will have this product, when we restore aromaticity, we're gonna have this product, and that's with a ketone. That's the Friedel-Crafts acetylation.
Biomolecular dehydration. Biomolecular dehydration is a reaction of mixing alcohol with an acid and heat. So an E1 reaction occurs, converting an alcohol into an alkene. And this dehydration produces useful yields of ethers. So now we have our alcohol reacting with an acid, H2SO4, in the presence of heat. So the alcohol will gain an H, producing a water molecule and a positive charge. So in the next step, the water molecule will leave, and we will have an alkane with a positive charge, ending up getting our alkene. Cleavage reaction. As we all know, ethers are very combustible but unreactive as a result of the two strong CO bonds that are not easy to break. So they can only undergo one synthetically useful reaction, which is cleavage in the presence of a strong acid. The acid must be super strong. It can only be HI and HBr. So here we have our ether reacting with HI, producing an I with a negative charge, which is a very strong nucleophile. So now the I will attack the carbon chain and kick out the OH as a leaving group. So here we have our alkyl halide and an ethanol. But the reaction doesn't end up there. Actually, the alcohol can react again by proton it with an HI. So here we have our alcohol and our HI reacting together, producing another I with a negative charge. So it will undergo the same reaction, and we will ending up getting two of the same alkyl halide plus H2O. Auto-oxidation. Ether can undergo auto-oxidation in the presence of light and oxygen. So here we have our ether in the presence of light. It will extract one hydrogen from the alpha carbon, giving a radical. And this radical in the presence of oxygen will give another oxygen-centered radical. From here we have two pathways to react with another ether molecule, giving ether hydroperoxide or organic peroxide, forming amines from nitrides. We will start with reaction between a cyanide and any alkyl halide to get our nitride. Here our cyanide, and the R here represents any hydrocarbon, and the X represent any alkyl halide producing our nitride. Then we will hydrogenate the nitrile using nickel or platinum as a catalyst. However, we need two hydrogen molecules to fully protonate the nitrile. So here is our nitrile reacting with two molecules of hydrogen in the presence of nickel as a catalyst, producing our primary amine, forming amines from alkyl halides, which is alkylation of ammonia. Here we'll start with ammonia reacting with a simple alkyl halide. Here is our ammonia and the simple alkyl halide, which is bromoethane. Since the ammonia is a basic molecule, so the pair of electrons on the nitrogen atom will attack the alkyl halide and kick the bromine out. Here the bromine is kicked out and the positive ion is produced. So by reacting the positive ion with another ammonia molecule, that will deprotonate the ion, giving our primary amine. So here our positive ion from this reaction will react with another ammonia, producing our primary amine. Note, if we have excess alkyl halide, ammonia will react again and our amine will be more alkylated. Synthesis of amines from amides. Amides can be synthesized from amides in the presence of a strong base. So here we have our amine, and here the lithium aluminium hydride. We'll start reacting forming a lithium with a positive charge and an aluminium hydride with a negative charge here, which is a very good base that will attack the carbonyl group, breaking the double bond as shown here. The double bond is broken. So this unstable intermediate will arrange itself so that the nitrogen will form a double bond and the CO bond will break and leave, giving two possible resonance as shown here in this reaction. So this product, which will react again and attack the cation, giving the desired amine.
Reaction with ketones or aldehydes. The reaction of ketones and aldehydes with amines form amine derivatives. They are known with Schiff bases. These compounds contain carbon double bond nitrogen function group. In the reactions that form amine, we must control the pH, preferably pH 5. That's because at high pH there will not be enough acid to protonate the OH. The reaction will be as follows. Amine plus aldehyde or ketone will give us amine plus water. Reaction as a proton base. Amines react as a weak base in aqueous solutions. Weak means partially dissociated in solution. Base mean it will accept hydrogen ion. Water in this reaction will act as acid or proton donor. Proton is transferred from water to amine. In this reaction we have amine, or in this case methylamine CH3 plus water will give us methylammonium plus hydroxide ion. This base will move here and the H will be transferred here. From alkyl halides via the nitrile. If alkyl halide is heated under reflux with a solution of sodium potassium cyanide, the halogen will be replaced by nitrile group and a nitrile will be produced. If the solvent contains water, the substitution happens by hydroxide group rather than nitrile group. In this reaction we have 1 bromopropane plus nitrile will give us butanitrile plus bromide ion. The bromine or halogen in alkyl halide replaced the nitrile group and this will produce nitrile or butane nitrile. Acylation of amines by acid chlorides. The acylation of amines with acid chloride produce one equivalent acid, which will form a salt with the unreacted amine. During reaction, we slowly add aqueous base to reaction mixture, and this is to neutralize the acid. The reaction is often named Schotten-Baumann reaction. We have acid chloride plus amine, while we also have NaOH that will give us amide. Alkylation of primary alkyl halides. Nucleophile is something which is attracted and attack positive molecules or ions. All amines contain active lone pair on the electronegative nitrogen atom. The reaction of amines with alkyl halide is a complicated series of reactions. The reaction must be done while heating to give mixture products, starting with primary, secondary, tertiary amines with their salts, ending with quaternary ammonium salts.